All right, welcome back to Talk Tensors. Today we're tackling a paper. Well, it's not just a paper. It's kind of hefty, honestly.
Oh, yeah.
Yeah, I mean, conceptually, it's trying to do a lot.
I can only imagine, given the title.
Right. System 0123. Quad process theory for multi-timescale embodied collective cognitive systems.
Okay, so right away we're talking about way more than just like individual thinking, right?
Exactly. So it's basically saying, look, this whole idea of thinking fast and slow, system 1, system 2, that's been so popular. It's not wrong. But
It's missing some pieces.
it's incomplete. It doesn't account for how much our bodies, our physical selves are part of intelligence. And then on an even bigger scale, how groups of people, societies, how that intelligence works.
Multi-Timescale, they say.
Mhm.
Which makes sense. I mean, think about it, a reflex, that's like instantaneous, but then language developing, that's over generations.
And this paper, it's trying to build a framework that connects it all. And they actually draw some inspiration from, Henri Bergson, the philosopher.
Interesting, not your usual AI paper citation.
Definitely not. But it gets at this idea of time, different kinds of time, which is key to their whole system. So we're going to try to unpack this. We'll go from the most basic, like a twitch, all the way up to how we make meaning as a whole culture.
Ambitious, to say the least.
Oh, absolutely. But that's why we're here, right? To dive into these big ideas.
Right into the deep end. So where do they even start with all this?
Well, they lay out their framework, system 0123. And the first one, system 0, this is where things get really interesting, I think.
All right, lay it on me. What's System 0 all about?
So it's like the intelligence that's baked in, like before you even think. It's embodied, super fast. They call it precognitive.
Okay, that's getting a bit abstract. Do they give any examples to make that clear?
Yeah, they do. Like imagine a simple toy, right? But it's designed so that just the way its legs are, the shape, it can walk down a hill, no motors, no brain, just physics.
Okay, so like the form itself is intelligent in a way, morphological computation, right?
Exactly. Or like those soft grippers they're using in robotics, the material is flexible, so it just naturally conforms to whatever it's grabbing.
Interesting. So it's not about calculations happening in a brain, it's about the way the physical world interacts.
Right. And they even talk about this thing called physical reservoir computing, where you actually use these complex dynamics, like, say, how an octopus arm moves, as a kind of computing resource.
Well, that's kind of wild. You're using the physics itself to do computation.
Yeah. So system 0, it's like this foundational layer. It's always there, influencing how the other systems work, even if we don't always realize it.
Okay, so that's our baseline. Then we move up to what we're more used to talking about, System 1 and 2, the fast and slow thinking.
Right, and they apply this to AI too, which of course is what we're all about here on Talk Tensors.
Yeah, how does that map onto what we see in machine learning?
Well, system 1, that's a lot of what deep learning's doing right now, right? Super fast pattern recognition, image classification, natural language processing, all that.
But we know those systems have their issues.
Oh, for sure. The paper talks about the limitations too. They can be very brittle, struggle with generalization, and often lack the kind of common sense reasoning that humans have.
So where does that put System 2 in the AI world then?
System 2, that's more like your classic symbolic AI, the logic-based systems, reasoning step by step, planning things out. Slower, but in theory, more robust.
And I guess the Holy Grail is combining them, right? This whole neuro-symbolic AI push we've been seeing.
Yeah, trying to get the best of both worlds. And the paper discusses some of those techniques, like learning disentangled representations, so the AI can actually understand the underlying factors of what it's seeing.
And using attention mechanisms too, right? Inspired by theories of consciousness to help the AI focus on what's important.
Exactly. And then there's this idea of representing knowledge as skills, like building blocks that the AI can combine and use in different situations.
So like giving the AI more of a toolbox to work with, rather than just brute forcing patterns.
Exactly. And of course, we can't talk about AI these days without talking about LLMs.
The large language models, yeah, everyone's buzzing about them. Where do they fit into all this?
Well, the paper mostly puts them in the system 1 camp. They're amazing at statistically predicting the next word, which is a kind of fast thinking, but
not necessarily deep understanding.
right. However, there are all these new techniques that are pushing LLMs to be more system 2-like. Things like chain of thought prompting, where you force the model to explain its reasoning.
Oh yeah, I've seen that. It's like trying to get the LLM to show its work, so to speak.
Exactly. And then there's self-refinement, where it can iterate on its own output and even using external tools, like with React and Toolformer, giving them access to calculators or databases.
So we're starting to see LLMs that can plan, that can have a goal and take steps to achieve it. That's definitely more of a system 2 vibe.
And then there are those LLM agents, LangChain, AutoGPT, all those. They're almost like little AI assistants that can reason over longer periods and manage tasks.
So even though the core of LLMs might be system 1, we're finding ways to layer on these system 2 capabilities. It's like we're giving them a forebrain, so to speak.
It's a good analogy. And, this whole framework, it's not just about AI. The paper also connects it to how biological brains work, specifically through this idea of neurodynamical systems.
Okay, now we're getting into the neuroscience. I'm curious, how do they bridge that gap?
Well, they discuss the work of Tani and his colleagues who use recurrent neural networks, RNNs, to model brain activity. And they've shown how these RNNs can exhibit behavior that maps onto the System 12 distinction.
I'm vaguely familiar with Tani's work. Didn't he do a lot with robots?
Yes. His earlier research involved robots developing simple behaviors, like reflexes, through their RNNs settling into stable patterns called attractors. And then he showed how adding forward models, basically internal simulations of the world, allowed the robots to navigate more effectively.
Right, so the robot isn't just reacting to immediate stimuli, it's predicting what's going to happen and planning its actions.
Exactly. And then his work evolved into these hierarchical RNN models, like RNNPB and MTRNN. The key idea is that different parts of the network operate at different timescales.
Okay, so it's not just a single network doing everything at the same speed. There's a hierarchy.
Right. So with RNNTB, you have a slower, higher level part of the network influencing a faster, lower level part. It's kind of like a system 2 controlling a system 1.
So the slow part could be doing the planning, and the fast part could be executing those plans.
That's the idea. And this connects to the concept of predictive coding, where the brain is constantly trying to predict what it's going to see or experience, and then adjusting based on errors.
Right, so it's not just passively receiving information, it's actively anticipating and making sense of the world.
Exactly. And then MTRNN, that uses different time constants for the neurons at each level, so it can self-organize into a hierarchy, with the lower levels learning basic skills and the higher levels learning to combine those skills.
Interesting, so it's a more flexible model. The hierarchy isn't predefined.
Yeah, and they've used these models to study all sorts of things in robots. Object manipulation, imitation, even language acquisition, and even more, they've extended these models to incorporate uncertainty, which aligns with the free energy principle in neuroscience.
That's pretty impressive, showing how these ideas can span from basic reflexes to higher level cognition.
And it suggests these models might be useful for understanding some aspects of mental health conditions too. So we've gone from the super fast system 0 through the individual thinking of systems 1 and 2, but then the paper takes a big leap to system 3.
Ah, yes, system 3. The realm of the super slow, where things get really, really big.
Right. This is where we go from individual minds to collective intelligence, the emergence of things like language, social norms, whole cultures.
Which seems kind of crazy to think about, right?
Yeah.
How do you even begin to model that?
Well, the paper argues that language itself is a tool for collective adaptation. The symbols we use, they're arbitrary, but they allow us to share information and coordinate in ways that no other species can.
And they tie this to the idea of collective predictive coding, or CPC. What's that all about?
So it's building on the idea of predictive coding in the brain, but expanding it to groups. It suggests that the emergence of language and other symbolic systems is like a decentralized way for a group to build a shared model of the world.
So it's not just individual brains predicting, it's like a whole group is collectively predicting and making sense of things together.
Exactly. And they give examples of how multi-agent systems powered by LLMs are being used to simulate virtual societies, like little towns where the agents interact and develop behaviors.
Kind of like those AI-driven video game characters that are getting more and more sophisticated.
Yeah, it's along those lines. And they talk about how LLMs can work together, like voting or combining their knowledge, and even engage in debates to refine ideas.
So it's not just individual AI, it's AI working collaboratively. Kind of like a hive mind, in a way.
In a way, yeah. And this all relates to the field of emergent communication, where they study how communication systems can arise from scratch just through interaction.
So starting with no shared language, just agents interacting, and then boom, communication emerges.
That's the idea. And CPC provides a potential framework for understanding how that might happen formally. The key shift in System 3 is that the learning is happening at the collective level, not just in individual brains.
And this brings us back to Bergson, right? His philosophy of time. How does that fit into all this?
Well, the paper spends a lot of time trying to interpret Bergson's ideas through this multi-timescale lens. Bergson saw time as this flowing, lived experience, what he called durée.
Right, not just clock time, but the way we actually experience time.
Exactly. And he argued that different processes have their own intrinsic timescales, like the time it takes for a thought to flash through your mind versus the time it takes for a mountain range to form. Those are totally different kinds of time.
And he also talked about the thickness of the present moment, right?
Yeah, that was a key idea for him. He said the present isn't just a razor-thin instant, but it has a duration, a thickness. And he linked that to our sensory and motor experience. Basically, the window of time within which we can act and perceive directly.
So not just the immediate now, but this short span where we're directly engaged with the world.
Right. And the paper argues that Bergson's ideas about time are surprisingly relevant to the System 0, 1, 2, 3 framework. For example, he talked about two types of recognition, one automatic, based on habit, and one more attentive, involving memory.
Which sounds a lot like the distinction between System 1 and System 2.
Exactly. And the authors link this back to the thinness or thickness of the present moment. System 1, with its fast automatic responses, is operating in a thinner present, while System 2, with its more deliberate thinking, needs a thicker present to access memories and plan.
Okay, that's a really interesting connection. So they're saying Bergson, way back when, was already hinting at these ideas about different modes of thinking operating on different timescales.
Yeah. And the paper identifies three key axes of timescales in Bergson's work. First, the different temporal layers within an individual, which might correspond to the four systems. Second, the timescales of adaptation, like how evolution or learning or even societal change happen over vastly different timescales. And third, the size of that present window itself.
And all of this is intertwined, right? The different timescales and levels are constantly interacting.
Absolutely. And then there's this fascinating idea that Bergson had about motor memory and what he called a canalized landscape.
Okay, now you've lost me a bit. What's a canalized landscape?
So Bergson distinguished between motor memory, which is our memory for skills and habits, and pure memory, which is our recall of specific events. He said that motor memory is geared towards action. It's about efficiency and automaticity.
Right, like when you learn to ride a bike, you don't have to think about every little movement. Your body just knows what to do.
Exactly. And the paper extends this idea, suggesting that motor memory can be seen as a kind of prior optimization, a way of offloading optimization over time.
Offloading optimization. What does that mean?
So think about it this way. Instead of having to figure out the optimal way to do something every single time, our brains and bodies have evolved to automate certain actions, to make them efficient and reliable. It's like we've outsourced the optimization process to our biology.
Okay, that makes sense. Like over millions of years, evolution has figured out the best way for us to walk, so we don't have to reinvent the wheel every time we take a step.
Exactly. And this canalized landscape is a metaphor for that. Imagine a landscape that's been shaped by water flowing over it for centuries. There are deep grooves, channels that have been carved out by the water. Those channels represent the optimized pathways of behavior that have been established through evolution or learning.
So we're not just wandering randomly across the landscape, we're following these predefined paths that have been optimized over time.
Right. And the paper maps this idea onto the four systems. So you have the fundamental laws of physics shaping the landscape at the level of System 0. Then you have biological evolution carving out the channels for species-specific behaviors. Then you have individual learning creating new pathways within our own brains. And then you have cultural evolution shaping the social landscape at the level of System 3.
Wow, so this idea of a canalized landscape applies at all these different levels and timescales.
Yeah, it's a pretty powerful concept. And they even link it to language. They say that language, with its ability to represent and share information across time and space, effectively extends our window of the present.
So instead of just being limited to our immediate sensory experience, language allows us to tap into this vast collective memory, this shared knowledge that's been accumulated over generations.
Exactly. It's like language creates this extended window of the present where we can access information and coordinate our actions in ways that would be impossible without it.
Okay, so we've covered a lot of ground here. Can we bring it all together? How do these four systems actually interact to create this integrated picture of intelligence?
Sure. The paper emphasizes that each of the four systems can be distinguished based on a few key features: the timescale it operates on, the type of representations it uses, the degree to which language is involved, the cognitive processes it embodies, the level of consciousness, and the scope of its interaction.
So System 0 is super fast, pre-representational, non-linguistic, reflexive, non-conscious, and primarily about physical interaction.
And then you have System 1, which is still fast but uses more basic representations, is mostly non-linguistic, relies on intuition and heuristics, is associated with a basic level of awareness, and involves interactions with the immediate environment.
And System 2 is slower, uses more abstract representations, can involve language, relies on deliberate reasoning and planning, is associated with higher level consciousness, and can involve interactions that extend beyond the immediate environment.
And finally, you have System 3, which operates on these super slow timescales, uses external symbolic representations like language, involves collective intelligence and cultural processes, might even have a form of superconsciousness, and operates at the level of social and cultural interactions.
So it's not just a linear progression from one system to the next. They're all operating simultaneously, interacting and influencing each other.
Exactly. It's the dynamic interplay between these systems, each with its own characteristics and timescales, that gives rise to the complex and adaptive behavior we see in individuals and societies.
And this interplay is what ultimately allows for things like symbol emergence and collective predictive coding to happen.
Right. The paper argues that it's not enough to just study these systems in isolation. We need to understand how they work together, how they complement and constrain each other.
And this framework seems to have some pretty big implications, not just for our understanding of intelligence, but for fields like cultural development, creativity, consciousness, and even robotics and AI. The paper touches on all of these.
Yeah, it definitely opens up a lot of new avenues for research. For example, when it comes to cultural development, they point out that traditional models often don't fully account for the interaction between cultural expressions and the environment in which they arise.
Right. It's not just about ideas spreading from person to person. It's about how those ideas are shaped by the physical and social context.
And they suggest that their generative MCOM framework, which is formalized within System 3 as CPC, could offer a more comprehensive way to understand how things like art and music and social norms evolve.
And they also highlight that creativity isn't just about generating new things. It's also about evaluation and acceptance within a social context,
Right.
which is something that AI models of creativity often struggle with.
Right. It's not enough for an AI to just come up with something novel. It has to be something that resonates with people, that has meaning and value within a particular culture. And that often involves emotions and embodied experiences, which are notoriously difficult to model in AI.
And then there's consciousness. The paper touches on some really deep philosophical questions about the nature of consciousness and whether it's something that can emerge at the collective level.
They draw on Bergson's idea that the experience of time might be fundamental to consciousness and suggest that the System 0123 framework could be used to explore the role of both embodied processes and collective processes in consciousness. They even discuss the idea of a collective unconscious, referencing Jung and Lacan.
Wow, so they're really going there. It's almost like they're suggesting that consciousness might not be limited to individual brains, but could extend to groups and even societies.
It's a pretty radical idea, but they make a compelling case. And then, of course, there are the implications for robotics and AI. The paper highlights the importance of both System 0 through the incorporation of passive dynamics in robot design, and System 3 with the use of language as a high-level control mechanism.
Yeah, I'm seeing more and more research on robots that are designed to exploit the physics of their environment rather than just relying on complex control systems. And using language to give robots more abstract goals and instructions is definitely a hot area right now.
They also talk about the potential for robots to develop their own unique forms of communication through embodied interaction, which would be fascinating to see.
It would be. And they suggest that System 3 itself could be seen as a kind of collective world model that robots could use to learn and adapt.
So it's not just about building individual robots that are smarter. It's about building systems of robots that can work together, learn from each other, and create a shared understanding of the world.
It's like taking the idea of swarm intelligence to a whole new level.
Exactly. So this paper is really trying to connect the dots between all these different fields and levels of analysis, from physics to biology to culture. It's incredibly ambitious, but I think it's also incredibly important. If we want to understand intelligence in all its forms, we need this kind of integrated multi-timescale perspective.
I completely agree. This paper has given me a lot to think about.
Me too. And now for our novel notions segment, where we take the ideas from the paper and run with them. What kind of new research questions or directions do you see emerging from this System 0123 framework?
Okay, so my first novel notion is inspired by the idea of System Zero and this whole concept of embodied intelligence. The paper does a great job of outlining how purely passive physical systems can exhibit intelligent behavior. But what if we could engineer systems that had just a little bit of computation embedded in them, something that could subtly enhance their morphological computation?
So not a full-blown control system, but just enough computation to nudge the system in the right direction.
Exactly. Imagine a soft robotic hand again. Instead of relying entirely on its passive flexibility to grasp an object, what if it had tiny sensors and actuators embedded within it that could subtly adjust the stiffness or curvature of its fingers based on the initial contact? It could optimize the grasp much faster than a purely passive response, but with significantly less computational overhead than a full-blown control system.
So it's like giving the physical system a little bit of intuition, a way to respond more intelligently to its environment without needing a lot of brain power.
Exactly. And this could be particularly useful for tasks that require delicate manipulation of diverse objects, like in logistics or healthcare. Imagine a robot that could handle fragile objects without crushing them, or pick up objects of different shapes and sizes without needing to be explicitly programmed for each one. And this idea could draw inspiration from the preflex mechanism in biological systems, which is faster than a neural reflex but likely involves some level of pre-programmed muscle activation. If we could successfully engineer these kinds of System 1.5 systems, it could lead to a new generation of robots that are incredibly energy efficient and robust in unpredictable environments.
That's a really cool idea. It's like finding a sweet spot between pure physics and complex computation. What's your second novel notion?
My second idea focuses on System 3 and the emergence of collective intelligence. The paper talks about collective predictive coding and the importance of communication for building shared models of the world. But what if we intentionally introduce communication bottlenecks in multi-agent AI systems to study the emergence of something like collective intuition?
So instead of letting the agents communicate freely, you would restrict the amount or quality of information they could exchange.
Exactly. The idea is that by forcing the agents to communicate more efficiently, we might see the emergence of more implicit, intuitive forms of understanding and coordination. Think about how a flock of birds can fly in perfect formation without any apparent leader or explicit communication, or how a group of musicians can improvise together seamlessly without needing to discuss every note in advance.
So you're thinking there might be ways for agents to develop a shared understanding without relying so heavily on explicit symbols and language.
Right? It's like they would have to develop a kind of shared feeling for the situation, a way of anticipating each other's actions and intentions without needing to constantly verbalize everything. And this could be really valuable in situations where communication is unreliable or too slow, like in swarm robotics or distributed sensor networks that need to respond quickly to a changing environment. And this research could also draw on ideas from information theory and data compression. By limiting the amount of information that can be transmitted, we might actually force the agents to develop more efficient and robust forms of communication.
Those are two really interesting ideas. It's amazing to think about the potential for discovering new forms of intelligence, both in machines and in ourselves, by exploring these different levels and timescales. And who knows, maybe we'll even uncover some clues about the nature of consciousness along the way.
It's definitely an exciting area of research. And of course, we always have to remember that these novel notions are just that. Speculative ideas meant to spark further thinking and discussion. They're for entertainment purposes only, but hopefully they illustrate the power of this framework to inspire new lines of inquiry.
Absolutely. So to quickly recap, today we dove deep into the System 0123 framework, an ambitious new theory that extends the classic idea of dual process cognition to include embodied intelligence and collective intelligence, all viewed through the lens of multi-timescale time inspired by Bergson. We talked about how this framework applies to AI, neuroscience, and even the emergence of language and culture. If you're interested in learning more, you can find a link to the paper in the show notes.
And the key takeaway is this. Intelligence is not just about what happens inside individual brains. It's deeply intertwined with our physical bodies and the collective systems we participate in. By considering these different timescales and levels of organization, we can gain a much richer and more accurate understanding of how intelligence works, both in the natural world and in the machines we create.
And on that note, we leave you with this final thought. Could truly understanding the interplay of these four systems be the key to unlocking genuinely human-like AI? Or perhaps even to gaining a deeper understanding of the very nature of consciousness itself? Thanks for tuning in to Talk Tensors, and we'll catch you next time.